have an aluminum calorimeter with a mass of 100 grams. It contains 250 grams of water. The calorimeter and water are in thermal equilibrium at 10 degrees Celsius. That just means they're both at the same temperature. 2 metallic blocks are placed into the water, and the system is sealed so no heat is exchanged with the surroundings. 1 metallic block is a 50-gram piece of copper at 80 degrees Celsius. The other is a block that has a mass of 70 grams and is originally at 100 degrees Celsius, but we don't know what it is, what the material is. The entire system stabilizes at a final temperature of 20 degrees Celsius. What is the specific heat of the second block? Now this type of problem is called the calorimetry problem. A calorimeter is basically a thermos type material. Thermos is made so that the energy, whatever you put in there, stays cold, or if you put hot stuff in there, it stays hot. It makes it so energy is not exchanged between the surroundings, the room, and the material inside. So it keeps the heat within the system itself. That means any heat exchange stays within the system. So having our aluminum and water at 10 degrees, but our blocks that are hotter, we toss them all in, seal it up so the energy can't be exchanged with its surroundings. If we add all the Q's, all the energy, because the blocks are going to get colder, the water and the aluminum are going to get warmer, but all of the energy exchange is between the objects that are within the calorimeter. So if we add all the Q's up, we're going to get 0. So the Q of the water getting warmer, the Q of the aluminum getting warmer, is going to be balanced out by the Q of the copper getting colder and the unknown getting colder. Does that make sense? So basically, we're going to say Q for the aluminum plus Q for the water plus Q for the copper plus Q for the unknown. All of that has to be 0. Some of the Q's are going to be positive, meaning energy is flowing into that material. Some of the Q's are going to be negative, meaning energy is flowing out of those materials. But all the energy is exchanged within these materials. None of it goes to the room that they're sitting in. So, Q, MC delta T. We need the mass of the aluminum, the specific heat of the aluminum, and the change in temperature of the aluminum. Mass of the water, C of the water, change in temperature of the water. Mass of the copper, C of the copper, delta T of the copper. Mass of the unknown, C of the unknown, delta T of the unknown. Those all have to add up to be 0. Since there's a mass in every term, it is okay to leave the masses in grams if you want to. And that's because there is a mass in every term. You can change it to kilograms, of course, as well. So the mass of aluminum was 100 grams. Specific heat of aluminum, you have to look on the table in the book. It is... Actually, if someone will look on the table in the book. I have mine in a different unit. Back cover of the book. Specific heat. It's bottom left-hand table. 385.
Oh, were we doing aluminum or copper?
Aluminum first.
That's copper, sorry. Aluminum is 900.
Just 900? Aluminum temperature change. The final temperature is 20 degrees Celsius. The initial temperature of the aluminum was 10 degrees Celsius. Change in temperature is always final minus initial. So 20 minus 10 is going to be 10. Remember, the difference in temperature is the same whether we write it in Kelvin or Celsius. Mass of our water is 250 grams. C of our water is 4190. Change in temperature of the water is also 10 Kelvin. It was at the same initial temperature as the aluminum and comes to the same final temperature. The mass of the copper is 50 grams. And you said 385 was the specific heat. Change in temperature for the copper. The final temperature is 20. The initial temperature was 80. 20 minus 80 is negative 60. That negative is important. That means the Q term for the copper is going to be negative. That means energy is flowing out of the copper. Mass of our unknown is 70 grams. The specific heat is what we're looking for. Delta T, final temperature 20, initial temperature 100, so we get negative 80 as our change in temperature. So we're going to bring this term to the other side, solve for all that stuff, divide by 70 times 80. That's going to give us our specific heat value. Let me know if you get a different answer. Thank you. So the grams, the unit grams canceled out in all of these. The kelvins canceled out. 1825, yeah. So we get the units of joules over kilogram Kelvin. So whatever this material is, it requires 1,825 joules of energy to raise 1 kilogram of that material by 1 Kelvin. Or you have to take out 1825 joules of energy to decrease its temperature by 1 kelvins. Questions on this problem? Yes?
How did you figure out what the temperature 10 was on those two right there?
Delta T is always final minus initial. Final minus initial. Other questions? So calorimetry problems, it's just an insulated system, so no energy happens with its surroundings. So if you add all the Q's, you end up getting a total of 0. Both of these Q's were negative, meaning they gave off energy. These Q's were positive, meaning they absorbed the energy and took it in. So the energy was all exchanged within the materials of the system itself. So calorimetry is a really good way to find specific heat of different materials. Specific heat is something unique to the material itself. And so you can use calorimetry to determine the specific heat of different materials.